The sum of the kinetic and potential energy of a test body in a gravitational field remains constant. The character of the motion and the type of orbit of a celestial body depend on the value of total energy. The parabolic velocity is the minimum velocity allowing a body to forever leave a given central mass. For bounded motion, the average kinetic energy is always equal to the absolute value of the total mechanical energy.
All right, welcome. Today, we're going to dive into a truly beautiful and fundamental concept in physics, how a single, conserved quantity, total energy, is the ultimate architect of every orbit. We're going to see how one simple principle dictates the shape, the size, and the ultimate fate of any object moving under gravity. So, here's how we're going to tackle this. We're going to follow a very logical path, starting with the bedrock foundation, the equation of motion itself. From there, we'll derive the law of energy conservation. That law will then naturally reveal the three possible types of orbits. We'll look at the ones that escape, the ones that are trapped, and we'll finish up with a really powerful result called the Virial theorem. Okay, let's start at the very beginning. Everything we're about to discuss flows from this single fundamental statement, the equation of motion for a body in a central gravitational field. This is really Newton's law of gravity, but written in the precise language of vector calculus. Now, this equation might look a little dense, but it's telling us two incredibly important things. First, look at the direction. The negative sign in the vector r tell us that the acceleration, that's dv dt, is always pointing back towards the central mass, m. Second, the magnitude. The 1 over r squared dependence, because 1r in the r cubed cancels the r vector, tells us it's an inverse square law. The pole gets weaker the farther away you are. That's it, direction and magnitude.
All right, now for a key move. We're going to take this equation of motion and perform a mathematical operation on it that will unlock something incredibly profound. This isn't just a random trick. It's a standard technique physicists use to hunt for conserved quantities. We're going to take the scalar or dot product of the entire equation with the velocity vector, v.
So why on earth would we do this? Well, you see, the dot product philosophy connects the force acting on the body with the body's actual motion. We're essentially asking the equation, how is the work done by gravity affecting the object's speed? This step is the bridge that takes us from the world of forces and vectors to the world of work and energy, which are much simpler scalar quantities.
And this is where it all comes together beautifully. Using a couple of simple identities from calculus, both sides of our new equation transform into time derivatives. The left-hand side, v dv dt, becomes the rate of change of 1/2 v squared, that's kinetic energy. The right-hand side becomes the rate of change of gm over r, that's the gravitational potential energy.
So, when we rearrange the terms, we arrive at this incredibly elegant statement. It says that the time derivative, the rate of change, of that entire quantity in the parentheses is 0. And think about that for a second. If the rate of change of something is 0, it means that thing is not changing. It is constant. It is conserved. And this is it. This is the law of energy conservation for an orbit. An orbiting body is on a cosmic roller coaster. Its speed, v, and its distance, r, are changing every single moment. As it falls closer to the sun, it speeds up, gaining kinetic energy but losing potential energy. As it climbs back out, it slows down, losing kinetic energy but gaining potential. But this equation tells us their sum, the total energy, E naught, remains absolutely constant through the entire trip.
Now we get to the absolute heart of the matter. The entire destiny of an orbiting object, whether it's trapped for eternity or on a one-way trip out of the system, is determined by a single piece of information, the sign, positive, negative, or 0, of that total energy, E naught.
This table lays it all out. It's a fundamental trichotomy. If your total energy is positive, you have more than enough kinetic energy to overcome gravity's pull. You're on a hyperbolic trajectory and you're escaping. If your energy is exactly 0, you're on the knife's edge. You have precisely enough energy to escape, coasting to a stop only at an infinite distance. That's a parabola. And if your energy is negative, you're in a gravitational well you can't climb out of. You are bound, destined to repeat your path forever in a closed ellipse. So let's look more closely at those first two cases, the unbound trajectories where the total energy is greater than or equal to 0. These are the flyby missions, the interstellar comets, the objects that are just passing through. Right, so for positive energy, you're unbound. Your kinetic energy is always winning the tug-of-war against the potential energy. As you fly away and r goes to infinity, the potential energy term minus gm by r goes to 0. This means that all that initial total energy, E naught, gets converted into pure kinetic energy, leaving you with a final constant velocity as you coast off into deep space. That special case, where E naught is exactly zero, defines what we call the parabolic velocity, or more famously, the escape velocity. It is the absolute minimum speed you need at a given distance r to just barely break free from the gravitational field. If you're going any faster, you're on a hyperbola, any slower, and gravity wins, pulling you back into an elliptical orbit. Okay, so we've seen how to escape. Now let's turn to the case that describes nearly every object in our solar system, the bound trajectories, which happen when the total energy is negative. This is the physics of planets, moons, and asteroids, all captured in stable, repeating orbits. For these bound orbits, their motion is perfectly described by this famous and powerful relation, the vis-viva equation. It directly links an object's speed v at any distance r to the overall size of its orbit, which we characterize by the semi-major axis a. And notice the connection. The semi-major axis is determined only by the total energy. The more negative your energy, the more tightly bound you are, and the smaller the value of a. This is the very definition of being bound. Your distance r is confined. It can never go to infinity. It's perpetually trapped between a minimum distance, called periapsis, and a maximum distance, apoapsis. You're forever on that roller coaster we talked about, trading speed for altitude and back again, over and over. Now check this out. This highlights a really neat and useful relationship. Let's say you're in a perfectly circular orbit. The speed you need is vc. The speed you would need to escape from that same distance is vp. And the relationship is simple. The escape velocity is always just the square root of 2, about 1.414, times the circular velocity. So to launch a probe from Earth orbit to the outer solar system, you only need to increase its speed by about 41%. All right, for our final section, we're going to zoom out and look at a powerful statistical result that applies to any stable, bound system held together by gravity. It's not just for a single planet, but for binary stars, globular clusters, even entire clusters of galaxies. It's called the Virial theorem. First formulated by Rudolf Clausius, the theorem reveals a deep truth. While the kinetic and potential energies are constantly fluctuating during an orbit, if you step back and calculate their average value over a long time, you find they obey a surprisingly simple and rigid relationship. So here are the results in equation form. For any stable, gravitationally bound system, the average kinetic energy turns out to be equal to the absolute value of the total energy. But even more famously, the average kinetic energy is always equal to negative 1/2 of the average potential energy. This fixed 2-to-1 ratio between the average kinetic and potential energy is a direct consequence of gravity's inverse square law, and it gives astronomers a powerful diagnostic tool. And this is not just a theoretical curiosity. This theorem is at the very heart of one of the biggest discoveries in modern astrophysics. When astronomers look at a massive galaxy cluster, they can measure the speeds of the individual galaxies. That gives them the average kinetic energy. Then they can count up all the stars and gas they can see and calculate the total gravitational potential energy. And the numbers don't add up. Not even close. The galaxies are moving far too fast. The kinetic energy is so high that the Virial theorem says the cluster should have flown apart billions of years ago. So what gives? For the theorem to hold, there must be a huge amount of extra mass in the cluster, providing the extra gravitational potential to hold it all together. Mass that we cannot see. And that is one of our primary pieces of evidence for dark matter.
Thank you, friends. Strive for understanding and become wiser. See you soon.